policies that produce a robot's behavior, either hand-coded or learned with associative learning, typically have an implicit causal structure. This can make it difficult to interpret what the robot is doing exactly, but also to perform effective, task-specific correction of the robot's behavior. An alternative representation that is slowly gaining traction is to use explicit causal models to produce behavior. Such models increase the introspective capabilities of robots, but are usually domain-specific, and their performance against already established methods is rarely evaluated. In this work, we consider the problem of robot navigation, where we deploy a model that is learned for social navigation. We use this model to score the quality of robot trajectories, but we also use it for performing online adaptation of the navigation behavior. Through this, our study proposes a complete framework which demonstrates the causal models are not just good to have, but also have real benefits for improving the behavior of a robot. In this paper, we adopt a previously proposed causal model for social robot navigation, such that we use this model as an offline trajectory evaluation module, but also as an online adaptation module that evaluates the robot's expected performance and intervenes if necessary. The causal model that we adopt is specifically learned to predict a human perceived competence, which serves as a proxy variable for the acceptability of the robot's behavior. Our proposed offline evaluation module uses the causal model to evaluate the competence of trajectories collected by a robot's default navigation stack. In our work, we analyze how this competence correlates with quantitative navigation metrics, concretely path irregularity, stop ratio, goal-directed progress, and path efficiency. During online adaptation, we predict the robot's motion based on the commands proposed by the default navigation stack and use the causal model to evaluate the predicted competence. If this falls below a given threshold, counterfactual reasoning on the causal model is performed to find motion commands that will increase the competence. To evaluate whether the model's predicted competence is actually a truthful representation of the model's behavior, we also compare the agreement of the predictions with human limitations. We evaluate our framework using a Pao Tiago robot, which moves through corridor segments. The map shown on the right illustrates the parts of our environment where the robot was moving during the experiment. For better diversity of the motions, we have three scenarios with increasing complexity: straight motion, navigation around corners, and navigation in scenarios where static or moving humans are present in the environment. We use the robot's ROS2-based navigation stack for collecting trajectories for the offline evaluation module, but also as a baseline online navigation components that we combine with the causal model for online adaptation. When adaptation during online navigation is necessary, the causal model produces velocity commands that overrides the commands proposed by the default navigation component. Here, we illustrate the robot's navigation behavior using the default navigation stack and with the active causal adaptation module. The video on the left shows the default navigation, which seemingly gets confused when a person is moving around and therefore gets temporarily stuck. On the right, we see the navigation with the active causal adaptation. When the person is approaching, the robot slows down instead of getting stuck, which is ultimately a more natural behavior. With our study, we show the potential of using causal models both as external observers that can evaluate the behavior of a robot, but also as components that can augment a robot's policy. Concretely, in the social navigation domain, we also demonstrate that predictive competence can be a useful proxy for evaluating the robot's navigation quality. Through this paper contributes to both increasing the overall adoption of causal models in practical tasks, particularly since we demonstrate that causal models do not need to be detached from existing components, but can instead be used to improve their performance beyond the scenarios for which they are originally developed.